Hello, welcome physics to your next flipped class lecture. As always, I'll just be on the slides long enough to describe them. If you need to pause to write things down, please feel free. And please use the comments field at the bottom on the blog page to ask me any questions that come up, and I will address them as soon as I can. We're in chapter 3 today. We're dealing with kinematics, which is the description of how things move. This is not math to predict their motion. This is just verbiage to describe their motion. Okay, so kinematics, a motion must be measured with relation to a fixed reference point. Your book gives a good example of this. If you were dropped into the middle of ocean and swam for an hour, how would you know that you'd gotten anywhere unless you could point to some kind of reference on land or a boat or a buoy or a dead whale or something and say, I'm further from that than I used to be, or closer to that than I used to be. So we always have to measure our motion with regard to a fixed point. We also have to keep our motion in reference to a number line of some kind, and we'll get more into that later. Okay, motion is defined as being in a different distance from a reference point at one moment in time than in another. And so I gave you some terms there. We're going to use X throughout this class to represent your placement, where you are with regard to a distance from a reference point. Okay, so X is a distance from a reference point. And then T is time, and that makes sense. Time is almost always referenced in seconds. You'll see some exceptions to that, but not very many. So we have an ordered pair set here, a coordinate pair. At a particular moment in time, you are a certain distance away from an object. At another moment in time, you are a different distance away from that object. Congratulations, you have moved. Okay, and you can graph that if you need to. We'll show some graphs in a little bit. Some terminology here. Distance versus displacement. So if you were to take a walk around a lake and you followed the shoreline, you would have covered a certain distance of actual path along the shoreline. But if, when you were done, we asked how far away are you from where you began, that's a displacement question, we could measure directly across the lake and have a different answer than how far you walked. So the path of travel gives you a distance. The difference in location is displacement. Okay, so a funny example is if you like to run track and you run around the track 8 times, okay, and you've done a lot of running. I don't know what a track loop is. Is it a quarter mile, half mile, something like that? Let's say it's a half mile, I don't know. And you run a half a mile around the track and you do that 8 times, you've run 4 miles, right? But if you start and stop at the same place, according to physics, you haven't run anywhere because your net change in location is 0. So that's the difference between displacement and distance. Distance is the actual path you take. Displacement is the net change in location. We will use a italicized S to talk about distance, and we'll use a boldface lowercase d for talking about displacement, and those are important. Notice that distance is always a positive number. You can't have a negative distance. If you're measuring how far something actually went, it went there. It didn't go not there. But displacement can be positive or negative depending on your point of reference. Okay, so just keep that in mind as well. Moving on. Scalar and vector measurements. A scalar measurement is a measurement that does not have direction in it. So examples of that would be, it's currently 73 degrees in my room. 73 degrees does not have a direction. It's not 73 degrees up or something like that, okay? So those sorts of measurements that don't have a direction are scalar. Generally, throughout your textbook, they are going to be using italicized terms to talk about scalar measurements, okay? Doesn't make it very easy for your note-taking because how do you write italics? You're like, but anyway, in your book, italics reference scalar measurements. And then the opposite of that is a vectored measurement. Vectors will become your friends throughout physics. You will be playing with vectors a lot. Vectors are measurements with a direction. So we're talking about 6 meters north of where I am right now, or 4 feet under my chair, things of that nature, where there's a direction as well as a number. Those are going to be referenced with bold characters in your textbook. So when you see bold terms, vector measurements. When you see scalar terms, italic measurements, okay? And we frequently reference vector measurements with a number line. And so we can put a number line down. Say you start at 3, you move to to the right 6 places, you move to the left 9 places. Where are you now? And so that will happen quite a bit, and we'll see some of that here in this lecture as well. Okay, some other distinctions we need to make. Speed and velocity. You are familiar with the concept of speed. Speed is tied to distance. How far did you go in how much time? And so that is a scalar measurement. It is always positive. You can't have a negative speed, okay? And it is looking at the distance covered per unit time. So the formula there for average speed is given to you. Here's one of the first equations you get to see. Yay, math! And work with just a little bit. So here we have a V for speed. Now notice this is an italicized lowercase v. That is speed, not velocity, which we're going to talk about next, okay? Speed. The bar over it, if you remember from algebra, a bar over a character means average, okay? So this is the average speed, alrighty, is the distance, S is the distance, divided by the change in time. So how far you covered and how long it took you to get there. You could also express that as the absolute value of the change in position over time. We can't have a negative distance, so that's why it's the absolute value. Bars are around it. And so it's always change in position, the absolute value of that divided by time. Now remember, you don't need to necessarily memorize these formulas. Some of them you're going to use so much you will memorize it because you're going to use it a trillion times. But I will always give you formulas on an exam. And on a quiz, and obviously if you're doing work out of the book, the formulas are there, okay? So don't worry about memorizing everything. Know how to use it and when to use it. There are 2 kinds of speed. Well, I guess 3, because don't do drugs. But the second kind of speed is average speed, and then the third one is instantaneous speed, right? So average speed is the average amount of rate, the average speed that you went over a certain distance, how much distance you covered, how much time. That's taken on an average. So on a trip, I'm going to drive 40 miles an hour for 3 hours, which I can only do in Hawaii if I'm driving in a circle. 40 miles an hour for 3 hours, and how fast is that on average? 40 miles an hour. Instantaneous speed is found at one point in time. So instead of looking at a trip over the long term, how fast did you go? Instantaneous speed is how fast are you going right now. And you are very familiar with a tool that gives you instantaneous speed, and that would be your speedometer on your car. Instantaneous speed is going to give you how fast you're going right now. There are sometimes trip computers and cars that will give you average speed for your journey, but that's not typically what we have, okay? We have instantaneous speed, how fast you're going this very moment. Now there's velocity. Velocity is going to be denoted with a bold-faced V, so that is a vector measurement. We care about a direction for velocity. Velocity is the measurement of displacement per unit time. So your change in position, but we care about overall displacement, not the path you took to get there, okay? The velocity may be positive or negative depending on direction. If I have decided that for a particular situation north is positive and you happen to be traveling south, then you have a negative velocity. Velocities are always an average. There's no such thing as an instantaneous velocity because velocity is displacement. Displacement is an average number, so you can't have velocity right now like you had speed instantaneously. Okay, the formula for that, very simple. Velocity average is equal to displacement over time. At the end of my day, I wound up 10 meters away from where I started my day, and it took 24 hours to have my life and get to that 10-meter location. I moved very slowly. 10 meters over 24 hours is very slow velocity, right? Or even worse, I woke up in the morning in my bed. I went back to sleep at night, back in my bed. I had 0 displacement for 24 hours. I moved very slowly in life. So just like you have a speed meter in your speedometer, this would be an example of a velocity meter. This is a weather vane, and the wind turns these little cups, and so we know how fast the wind is moving, but we also capture the direction of the wind with this weather vane. So this would be a velocity meter, whereas this is a speedometer. This speedometer doesn't tell you you're going this fast north. You may have a trip computer that does that separately, but that's not the point of this device. Okay? Velocity takes direction, speed does not. Speed can be instantaneous, velocity is always average because it's always displacement. Alrighty, moving on. So we have some other terms, to describe motion. We have acceleration. Acceleration is the last term here that we need to get a grip on. Acceleration is the change in velocity over time. So just like you have change in location over time, that's speed, and displacement over time, that's velocity. Now we have a change in velocity. At one moment in time, you're going 6 meters a second. At the next moment in time, you're going 48 meters a second. The change between those two velocities is acceleration, okay? And so very simple equation for this as well. We have change in velocity over time, that can be instantaneous acceleration. At this moment, I am accelerating at a particular rate, or it can be average acceleration. Over the course of my whole trip, I accelerated an average of this, okay? Acceleration can be measured instantaneously or as an average, and it can be positive or negative depending on if you're speeding up or slowing down. So let's show you some pictures to help you understand this. This is a position versus time graph. So this means that at point 0, I am at my reference point. 40 seconds later, I am 400 meters away from my reference point. Then I stand there for a couple of seconds, for 30 seconds, and then I start to walk back for 20 seconds, and then I run the rest of the way home in the next 10 seconds, okay? This is a position versus time graph. You can get speed from this because you're looking at the rate of position change versus time, okay? This is another example of position versus time. Here, I am smoothly accelerating throughout my journey so that I started at my reference point and ended a good long ways away from it, and I was going faster every moment of my journey. Alrighty? So that's an example of that. Now, we can talk about displacement on these two trips and get very different answers. Because I started and ended at my reference point, there's actually 0 displacement here. It's like waking up in your bed and going back to sleep there. You did nothing during the day. I don't know why you're tired. This is a positive displacement, right? I started at my reference point. I ended somewhere else. So this has a velocity. This has displacement. This journey with 0 displacement would have 0 velocity, okay? Some other things to look at here. Here's a couple of different examples of distance versus time or displacement graphs, different things that you can see in these graphs. Fast, steady speed, you are going further away as time goes on, and it's a constant rate of speed. So this is fast, steady travel. This would be a steady speed and then stopping and then going back home, like that first graph that we saw. And this is an example of getting faster and faster and faster as time goes on. That's an acceleration curve. Okay? So take a moment, pause the video, look at those, make sure you understand what those are showing you. And now we have some velocity graphs. Now this looks similar, but notice it's velocity, meters per second squared, meters per second, not distance from my origin, and then time. So this is not, I'm getting further from my reference point. This is, I am accelerating, because this is how fast I'm going now over time. My speed is going up, I'm accelerating. Now I'm not standing still, which is what was happening here on the distance graphs on a flat line. I'm traveling at a steady speed. I'm getting on the freeway, I'm accelerating, and now I'm driving at freeway speeds. I'm just cruising along, okay? Then I hit traffic, so I need to slow down. And that's deceleration. The line goes down. And then the traffic breaks in front of me and I'm running late and I need to get there quickly, so I floor it. And I've got increasing rates of acceleration, and up here I get a ticket. Okay, so velocity versus time. Pause the video, take a look at this, make sure you understand the difference between velocity